I'm going to talk about the use case about ingestion, streaming ingestion from Apache Kafka to Apache Iceberg data lake table. The main topic is the schema evolution. So I mean similar schema evolution for streaming use cases. Before starting this content, how many of you are actually already using the Apache Iceberg? Oh, thank you. Thank you for the feedback. So I am really happy to see the Iceberg users. And if you are not familiar with Apache Iceberg yet, then I'll try to cover as far as possible that I can. Okay, cool. Or let's get started. I'm Noritaka Sekiyama, the big data architect belonging to the AWS GRU, the service product team. I'm responsible for building software artifacts that help customers to build cloud on AWS. I'm also helping customer architecture as well. That's the reason why I come here. And here's some of my publications. Today's agenda. So first, I will talk from the common challenges in the streaming data processing, especially in streaming data ingestion. Then I will demonstrate the several options to ingest into Apache Iceberg from Kafka. Then in this session, I will do two different demos. Then finally, I will cover the few best practices about the schema evolution with Apache Iceberg. Okay, then first, I will start to recap the common challenges in schema handling. So one of the common streaming use cases is streaming data ingestion from streaming source like Apache Kafka into data lakes. Maybe some of you attended today's keynote session, and we saw a lot of the different things about data lakes and the streaming data integration with Iceberg. In this kind of the use case, the records in the data source are sent to Kafka, and the records coming from Kafka are ingested into data lakes, commonly on cloud-based storage. And you saw some examples in yesterday's keynote as well. When we focus on schema of the data, there are three major challenges in schema handling. The first is schema evolves over time. The second, records can be invalid. Third, the streaming processing should continue without any interruptions. Let's look into each of them one by one. Streaming data ingestion often has to deal with the evolving data format. I mean, schema of the incoming records can change over time as the new attributes get added by producers. For example, let's take a look at the slide. Originally, there are three different fields. This is similar to the quick stream data. And the first record is session ID. The second record is timestamp. Third record is page URL. This is very common structure in a quick stream world. But after some time, the producer decided to add one more column called quick type. This kind of column addition or deletion or change of the data type is super common in streaming data processing. We need to handle this kind of schema change in any of the streaming use cases, usually. The second topic is that invalid record, I mean low quality data needs to be validated and need to be isolated as well. These kind of records should not impact any downstream applications, like for example, the Snowflake, Athena, Redshift, or if you are the consumer, you shouldn't be impacted by this kind of the low quality data, even if there is some poor data. For example, there are three different examples in this slide. The first one is missing column. Take a look at the left top left example, there are 3 different columns. Hope you can see the characters. But there is one missing field called page URL. In this example, the page URL is one of the mandatory fields. If you are missing this mandatory field, this can be categorized as an invalid record. The second example is the top right. There is the quick type field, or it has scroll as a value. But in this field, I define this field to be 3 different values, like page click, page visit, and button, and link. If you see something different in this field, then this can be categorized as invalid field. The third example is more simple, the invalid data types. You see the timestamp field has the ISO format, like 2024, 920, it was 980, 18, or something like that. But if you define this field as a unique timestamp, like it has long or big int feature, then this can be recognized as an invalid record. Even when you see the invalid record or schema evolution, the streaming processing should continue without any interruptions. So you cannot expect a downtime in most of the use cases. It means graceful handling of schema changes and data errors is very critical for zero downtime in modern near real-time data platforms. As a summary, there are mainly 3 different considerations in terms of the reliability. The first is schema evolution, the second is partition evolution, and the third is invalid record detection and isolation. Now we understand the common challenges in the schema handling. And we also understand the reliability considerations for that use case. Then let's discuss how and why the Apache Iceberg is a good choice for this kind of seamless schema evolution. Apache Iceberg is one of the common open table format that allows you to achieve the flexible schema handling. It also supports the additional capabilities such as AC transactions, time travel, and so on. The Iceberg is the ideal choice to enable seamless schema evolution and very strong reliability for streaming workload. Especially, Iceberg allows you to add new columns or modify the existing column types over the time without any downtime. Apache Iceberg manages this by creating new schema versions, and it evolves the table metadata at a commit time while keeping the existing data compatible and accessible for any applications. Old data and new data files with respective schemas coexist together with Apache Iceberg. So if you think more about schema evolution, Apache Iceberg allows you to make changes in the table structure design. And it allows you to update only metadata. It means you won't touch the actual data files. It enables you to operate the new and old data, old table structure seamlessly. So especially for the schema evolution, there are several different subcategories for schema evolutions, but Apache Iceberg supports most of the capabilities, such as add column, drop column, rename column name, and reorder the columns as well. And also, if you are familiar with data lake technology, the partition structure change is a kind of significant operations, But with Apache Iceberg, you can change the partition columns or partition column structures afterwards. It's a really big value with Apache Iceberg. You can also change the sort order and column change orders as well. If you really want to understand how Apache Iceberg works in details, in action, it is really important to understand how Apache Iceberg table is structured. This is a little bit dive deep slide, but I will try to do my best to explain this. So first, the Apache Iceberg table design is defined in Apache Iceberg table spec. This is a publicly accessible document. You can take a look. And commonly, the latest version is table version 3, but many customers are using table version 2 or so. Any engine that supports Apache Iceberg follows this table spec, which is defined by the community. And let me go back. There are mainly 3 different layers in this table design. The first layer is Iceberg catalog. The second layer is metadata layer. And the third layer is data layer. Let me explain one by one. The first layer is Iceberg catalog. Iceberg catalog manages the namespaces. It means the set of the set of tables. And this actually points the location of the latest metadata file. And if you update the Iceberg table, then Iceberg also updates the table metadata file located in this place. The one important fact is that the Iceberg catalog itself doesn't have any metadata. It's just a pointer. So it just has a location of the metadata file. So it's very different from the Hive metastore. So if you are familiar with Hive ecosystem, then please be careful or not to be confused with this concept, as there is no direct relationship between Iceberg catalog and Hive catalog. The second layer is the metadata layer. This is the most important layer for today's topic, like schema evolution. So metadata layer has 3 sub-layers called metadata files and metadata manifest list and manifest files. These 3 are called as metadata layer. And this layer tracks all the operations happening for this Iceberg table. And this layer is used for any Iceberg-specific operations like time travel, schema evolution, and so on. And this is one of the sub-layer called the manifest file, metadata file. And metadata file manages the table metadata in JSON file format. And it has the several fields such as schema history, the current snapshot, and snapshot history as well. And each table update will create a new metadata file. So if you update a table, then it will populate a new metadata file location, and the Iceberg catalog will be updated by this new metadata file location. That's how Iceberg works. And let me show you one of the example file I generated last week. This is one of the sample metadata file. If you can see, there are 3 columns defined in the schema's value. But if you scroll down, then you see the schema again. But this next schema has 4 columns. It means I added one more column later, but the metadata file itself has entire history of how my schema evolved over time. And the last layer is the data layer. Data layer is actual data file. The Apache Iceberg are used to store data in different formats such as Parquet, ORC, or Avro. But most of the use cases use Parquet, as far as I know. And it also supports the delete file vector in this place. This is how the Apache Iceberg data table is constructed. And this is a summary of the individual layer. But the important thing is just 3 things. Iceberg catalog has location, The metadata file has its schema and its history, and data layer has the actual data. That's the simple conclusion. Now, what are the options to ingest data from Apache Kafka to Iceberg? How can we ingest data into Iceberg format? There are several different ways to achieve that. If you attended in today's keynote, day 2 keynote, the keynotes talked about the table flow. Table flow will be the fourth option, I believe. But I will focus more on the open source side in this session to showcase what are the common options. The first option is Kafka Connect. If you are familiar with Kafka ecosystem, you are also familiar with Kafka Connect, I believe. The Kafka Connect is one of the Kafka ecosystem's component. You don't need to write any custom code or just to write Iceberg table. And you can achieve, of course, the exactly once semantics. And if you want to use the Kafka ecosystem fully compatible with the existing ecosystem, then Kafka Connect is still a very good option to ingest data into Iceberg. What you need just to import the Iceberg sync connector to Kafka Connect and use it together. The second option is Flink. The Flink is now super common engine for the streaming processing. And you can also achieve Iceberg ingestion with Flink with very low latency and exactly once semantics. The third option is Apache Spark. The Apache Spark is designed for the batch streaming use cases, and it is good for complex transformations or joining multiple sources coming from different things, such as relational databases, SaaS application, and so on. I will choose Apache Spark for today's demo or perspective, but all the design patterns and the concept are applicable also for other options. I will choose Spark for just as an example of how to ingest data to Iceberg. Let me explain a little bit more about Apache Spark. The Spark has a feature called Spark Structured Streaming, which is designed for the real-time streaming processing. It can read from Kafka, Kinesis, S3, HDFS, and do some micro batches. That's how Apache Spark works. And if you want to use Apache Spark with Iceberg, it's not very difficult. So the first half of the code snippet is how to read from Kafka. So in this place, I am creating a new data frame. A data frame is a very similar concept to table. I am using Python. Then I am writing into some place. To do that, I am calling process batch UDF inside this Spark function. And process batch function is something like this. So first, I retrieve data from Kafka into the Spark data frame, then write into Apache Iceberg tables. That's it. You may be confused a little bit about the number of lines of code, but technically speaking, it's very simple code snippet to achieve the data ingestion in Spark. Okay, now we understand how to use Spark structured streaming for Kafka and Iceberg. And then next topic is how we can use Apache Iceberg with Spark, because the Iceberg works very well with Apache Spark. So that's the reason why I am using Spark for this session. So if you want to use Iceberg with Spark, that's very simple. What you need is to provide the required jar file to the Spark runtime. The Spark submit is the command to trigger the Spark applications on the cluster. And what you need is just to provide a jar file in the argument. Then in your script, you need some configuration very specific to Apache Iceberg. Then that's it. then you can run whatever you want for the Apache, your Iceberg table. In Spark, you can run the Spark SQL, which is a standard SQL or compatible with ANSI SQL. So or you can run, for example, alter table, add column, or rename column, or alter column type, or for the schema evolution perspective. You can also change the partition or column order or add partition column by using Spark SQL. That's how the Iceberg table can be operated with Apache Spark. Then what happens when you try to ingest incompatible data into the destination Iceberg table? By default, it errors out. This is some of the error messages I got last week. And the first error is something like, for example, the destination table has only 3 columns, but my incoming data has 4 columns. It means the data are inconsistent and incompatible format. If so, then it will error out. So this is the default behavior of the Apache Iceberg table. But of course, there is a way to avoid this kind of situation. In this session, I call it as dynamic schema merging. This can be done by Flink or Kafka Connect, but I am talking more about how Spark is doing so. So while inserting or updating record into Iceberg table, you can achieve the dynamic schema evolution over time. If you enable this, then here's how it works. There are 2 operations. The first one is a new column is present in the source incoming records, but not in the target Iceberg table. Then what happens is, take a look at the bottom figure and tables. So see that there are 4 columns, but the target table has only 3 columns. Then the Iceberg automatically adds 1 more column and adds the value that is included in the source incoming records. This is very natural behavior, right? Then the second is that the column is present in the target Iceberg table, but not in the source. Then what happens is that, for example, there are only 3 columns, session ID, timestamp, click type, but the target table has another column, like page URL. Then the Iceberg automatically insert new for this column, then achieve the schema evolution. This is how dynamic schema evolution works. And to do that with Apache Iceberg and Apache Spark, what you need is 3 different operations. The first, you need to provide the 1 options written at the top. The second, you need to configure your table or to accept any schema. The third, when you write into Iceberg table, you enable merge schema options through data frame. Those 3 are only the options you need. Then you can achieve the automatic schema evolution. So let me demonstrate how it works in the real world. Before showing the demo, let me explain the common strategy. For schema evolution strategy, mainly there are 2 different strategies. The first one is source schema is always correct. It means that Iceberg schema is always updated dynamically at the destination because source is always true. So incorrect records with the incoming data needs to be validated or removed afterwards. This is the first strategy. The second strategy is the target schema is always true, always correct. It means any incompatible data coming from source will error out. And Iceberg schema needs to be maintained and managed explicitly and manually. So I will choose the first schema evolution strategy, like source is always correct for the first demo purpose. And here I am using AWS Guru service, which is our serverless data integration service running on top of Apache Iceberg. But I will use Guru just as a runtime of Apache Spark. So you can use vanilla Spark, you can use other Sparks for the same purpose. Here's a demo scenario. So in this demo, I'm going to showcase the stream data ingestion from Kafka to Iceberg table on S3. The schema strategy is source schema is always correct. So if you look at this, there we have some component. The first component is MSK, Amazon Managed Streaming for Apache Kafka. I'm using this as a Kafka runtime, but there is no difference between open source one. And Kafka, Spark, S3, and that's it. Then I am going to use Athena for explanation perspective to showcase the tables. In this demo, at first I will start sending sample records, then start the Spark streaming job to consume data from Kafka and write to Iceberg. Then I will showcase the records through Athena. Then I stop the recording. Then I will add one more column. Then start sending record again. Then show the Athena to see what's the difference. Let me start the demo. This is the Amazon Managed Streaming for Kafka console. And here's my Kafka cluster that I created. This is corresponding to Kafka 3.5, and this is running in my account. Now going to the AWS Guru console, which this one is to consume data. This is the example of the Spark streaming data. So Spark streaming script. So this is consuming from Kafka and writing to Apache Iceberg. So once I run this, this is already running for a while, then it means that Kafka records are now going to be consumed by this streaming job. And I also need some sample records, so I have another separate Guru job to send some record here. In this sample, I am sending the similar samples like quick stream samples, session ID, timestamp, and page URL. Now I started the job, so the data is going to Kafka. Then Kafka data will be consumed by Spark streaming job, then write to S3. Now we are seeing from Athena that we have 3 columns with the sample records, and it is now going to be ingested continuously. So it means you will see the number of increased records. Right now, it has 396 records, but for time being, then you can see more and more records, like 430. Now, it shows how the dynamic schema merging works with this demo scenario. Okay. Now, next demo is more advanced demo pattern with WAP pattern. WAP pattern is something I will explain later. In previous demo, I said there are only 2 strategy, but I am going to introduce one more strategy here. So schema is validated dynamically in WAP pattern. In this pattern, the data quality is the main focus. Data quality rule checks any incoming record to see if this is compatible with predefined rules. If it is not compatible, then we don't ingest. But if it is compatible, then we ingest and evolve the schema dynamically without any manual operations. So this is more careful strategy, but it still keeps dynamic merging. So this is one of the realistic options in the real world. And in demo scenario, The WAP, let me explain the WAP pattern. The WAP pattern means write, audit, publish pattern. This pattern is designed to ensure the data quality in your streaming application. And it is not just for streaming. Actually, it is designed for any data platform. It avoids the data quality issue. I mean, it avoids detecting the data quality issues at the consumer side. Because, if you have the data quality issue at the end, for example, you get some escalations from your end users that, oh, I am getting no from this my query, which didn't happen 3 days ago. What happens? Or something like that. We really want to avoid this kind of situation because it is more difficult to detect and recover at the consumer side. And the best strategy is to detect this kind of issues as soon as possible in the very early phase of the data processing, then do something proper handling. And this pattern, WAP pattern, is very similar to what we have in the CI/CD pipeline. So please take a look at the bottom diagram. When data writer ingests data to the table, the first operation is write. But the important portion of this is that you are writing data to staging branch. So there is a concept of branch. Now, the next operation is audit. You audit the records that is ingested in the staging branch. Then, once you validate it and you confirm that your records has very high quality data, then you publish data from staging branch to main branch that is accessible and visible from the consumer application. This is the main concept of WAP pattern. In the WAP pattern with Apache Iceberg, I use the concept of Iceberg branch. Iceberg branch manages your data for the various environments with different configuration. The branch feature provides Git-like experience for your data management. It enables you to create a new branch or switch branch from some branch to another branch, very similar to what you are doing with in day-to-day life with Git. And it also allows you to fast forward data to the branch. So let me explain that in several operations. If you want to create, if you want to configure a WAP pattern, what you need is to provide the table property to notify Iceberg table to be aware of this is a WAP enabled table. And you can also create any branch using Spark SQL, and you can set the current branch to the specific branch. If you want to read from the specific branch or write into specific branch, you can also use the identifier, like the prod db sample branch audit. So prod is a catalog name, db is database name, sample is table name. And if you have branch underscore branch name, then it means that it corresponds to the specific branch using this identifier. If you implement WAP pattern with Apache Iceberg branch, then what you do is something like this. So we'll first create an audit branch. The second, set the current branch to the audit branch. Then third, you write new records into, for example, the 2024 or September 18 branch, under 18 table or under the audit branch. Then after writing data, you validate the data in the audit branch. You can do all this with any preferred data quality framework. In this session, I am going to use AWS Guru Data Quality, but you can choose whatever you want. Then you fast forward the branch data from audit branch to main branch so that your consumer application can read the already validated data through main branch. AWS Glue data quality is a feature that is provided by AWS Glue, which is a serverless data integration service. It allows you to check the data quality in different phases of the data platform, and more importantly, it can detect anomaly based on the ML algorithm. It supports also dynamic rule definition, which is really useful for trending use cases, right? For example, your threshold needs to be updated continuously. It supports such kind of operations, and you can easily define the data quality with Glue data quality. And let me explain a little bit more about that. So if you want to define one column, like for example, you want to validate if the country column has one of the three values, like US, Canada, and the UK, then your rule will be something like this. So column value, country in US, UK, and CA. This is a simple definition of data quality. But if you want to detect anomaly, like for example, you expect a column number, you want to detect the column number changes. So if right now you have the 3 columns, 4 columns, but if you see 100 columns, then something happened. If you want to detect this kind of anomaly, then you can just say analyzer equal column count. Then you can easily detect anomaly. In this scenario, so let me go back to the demo 2. The scenario is same. Stream data ingestion from Kafka to Iceberg, but strategy is different. Right now, we are using WAP pattern, so source schema needs to be validated. So I added one extra Spark job just for WAP pattern. So I am writing from Kafka to Iceberg table using staging branch. Then I validate data through audit branch, then publish to main branch so that Athena can read. So the demo scenario is very similar, but I am going to send some invalid record as a sample. So the sample records now include some invalid data to showcase the poor data quality. Then I also start the Spark streaming job to consume data from Kafka to Iceberg. Then see records from Athena. Then I will run separate Glue job to do the validation and also fast forwarding the data from staging branch to main branch. Then check the result. So let's see. So this is another producer for the generating sample record. If you scroll down, then let me start. Okay, it's now starting. So if you scroll down, there are 4 different columns. And in the 4th column, I am using 4 different values. It's very difficult to see for you, but I am sending 4 different values. And one of the values is an example of the invalid record. Now I am running a separate consumer job, which is Spark streaming job, to consume data from Kafka and write into the destination table using staging branch. Now I am using branch underscore stg. It means that I am going to ingest data into staging branch directory. Now I am running this consumer application. Now it's running and it's consuming from Kafka and writing to the destination Iceberg table. Let me see what records we see from EMR at Spark. In the staging branch, right now we have 183 records, and we see the records like this. And the important point here is that it has some invalid records having scroll in click type. It's an example of the invalid record. Now, if you take a look at the main branch instead, that was a staging branch. But if we take a look at the main branch right now, then we see only 21 records right now. Okay, this is the baseline. This is the starting point. And if we take a look at the destination table, we also see that only 21 records are the destination because staging branch has a lot of records, but main branch has only 21 records. Now, after a while, we see the staging branch number. Then before that, it has 180. But right now, we have 216 maybe? 216 maybe. And we have more and more records over time in the staging branch. Then we run the separate WAP job to audit the data that is written into staging branch. Then we are reading from staging branch. Then we are running glue data quality check to see if we have the expected schema. And for example, the click type column has the valid value, which is corresponding to 3 predefined values. Then after that, I am ingesting only the successful records to the main branch. That's how I am fast forwarding the data to the destination. This is how the WAP job is built. So now it's time to, this is the record that is containing the successful record. Then in this line, I am writing the successful record to the destination. Let's run this job. Then this job will take a while to complete and validate the record in the audit branch, then do the fast forwarding. Now, after a while, we see that this job completed successfully. Now, when we see the destination main branch, then we see 225 records at the destination Iceberg table. It is significantly more than what we saw in the previous step. And you notice that click type doesn't have scroll in the value. It only has 3 different values, which are correct values, because we already validated the data quality when we ingest data, when we fast forward data to the main branch. If we do the group by based on the click type, then you notice that there are only 3 click types here. So you can see that the main branch doesn't have any poor quality data at the destination. But if you want to see more in the staging branch, then you can run the same query through through Spark. Then you will see the more and more records in the staging branch. So staging branch is still accepting any data, any poor data. So the number of the records is still growing. But once we are validating the records in the WAP pattern, so that's the reason why the main branch doesn't accept this kind of poor values, and the main branch still has the 225 records, and it has only the high quality data. That's how the WAP pattern can be done in this scenario. I have only 1 minute, so let me summarize, add one more topic about the schema evolution. This is the best practices for how to manage a schema evolution. But there are 2 different things you will need to consider: the backward compatibility and the forward compatibility. Backward compatibility ensures that the new schema can interpret the data written in the old schema. You mean, for example, you need to be careful to add new columns as nullable, or you need to be careful to set the default values. Otherwise, it can easily break the existing data and existing downstream applications. You also need to avoid renaming or removing the column which is currently used by the downstream applications. And you also need to be careful not to modify the type of existing columns. This is important topics for backward compatibility. And here's the important topics about how to manage forward compatibility. So forward compatibility ensures that the older schema data can interrupt the data written in the newer schema. To do that, you need to avoid adding the non-nullable columns, not to break the existing workload, and you need to provide backward compatible view to review access. To help the existing customers, you will need to provide backward compatible view for the simplicity. And especially for both forward compatibility and backward compatibility, it's very important to keep documenting the changes so that end users can understand what are the changes. That's it. So in this session, I demonstrated how you can achieve the seamless schema evolution using Apache Spark. And I used Apache Iceberg as a core engine, and Apache Spark as an example on the engine. But you can apply the same concept to any environment using Apache Iceberg. I hope this session helps your workload.